In this video, you will learn about the essential differences between plastic and elastic structural behavior. Plastic analysis allows for more efficient structural design as the basic cross-section capacity is increased over elastic design. Using some of the concepts that will be taught in this part of the course, plastic analysis can simplify the analysis of complex structures. Finally, plastic analysis also allows for the provision of some reserve capacity useful in extreme loading scenarios such as blast and impact. To understand the plastic response of a structure, we consider a cross-section of a structural element undergoing bending. Initially, the strain is set to a value epsilon1, which is less than the yield strain epsilon y. The corresponding stress distribution has a value of F1 for the extreme fibre stress, which is less than Fy, the yield stress. We can plot this point on a stress-strain graph where we have epsilon 1 and F1. The slope of this line is the Young's modulus, or modulus of elasticity. If we increase the strain to epsilon 2 and say that this is equal to the yield strain, then the corresponding stress will be F2, which is equal to the yield stress. If we plot this on the stress-strain curve, we get the following. Epsilon 2, which we set equal to the yield strain, and the yield stress, which is also equal to F1. And this is just a continuation of the line that we drew previously. If we now extend the strain beyond the yield strain, the yield stress at the extreme fibre of the cross-section remains the same at Fy, but we now see that the material throughout the cross-section starts to yield. That is, we say, the yielding is penetrating the cross-section. On the stress-strain curve, as the yield stress is not increased, the value of F is still equal to Fy, but corresponding to this is the increased strain of epsilon 3. Between these 2 points, we then see what we call a yield plateau. If we continue to increase the strain to epsilon 4, which is set equal to epsilon s, beginning of strain hardening, then the yield will continue to penetrate the cross-section until the section becomes fully plastic. The corresponding point on the stress-strain curve is, as before, we have an extension to the yield plateau and the corresponding strain of epsilon 4 equal to epsilon s. If we then extend the strain beyond the initiation of strain hardening, the material actually strengthens and we say it is strain hardened. The corresponding stress distribution then shows an increase in strength over the yield strength, and correspondingly the stress-strain curve starts to develop a secondary slope as shown on the stress-strain curve. The slope of this curve is given by ES, and we call this the strain hardening modulus. The process of strain hardening is caused by the generation and movement of so-called dislocations in the material's crystal structure. To visualize the process of strain hardening, consider the following single crystal lattice typical of a metallic material. Each atom is bonded to the one next to it, where the atoms are indicated by the circles and their bonds by the lines. And this is showing the system at a state of zero strain. As force is applied, layers of atoms slip over one another, breaking the bonds, causing plastic deformation. You can see here that the bond has been broken, and this forms what we call a slip dislocation. This dislocation is indicated by this symbol that looks like an upside down T. As we continue to apply the force, the dislocations travel along a plane. This plane is called the slip plane. As more force is applied, additional dislocations are created, and these are shown in green. Dislocations moving in the same slip plane will meet and repel each other. This creates additional resistance in the crystalline lattice, hardening the metal and causing a reduction in ductility. For the purpose of this course, plastic behavior can be idealized by neglecting strain hardening. As a consequence, we start with an elastic distribution of stress for a given cross-section. And once it reaches the yield point, as before, yielding starts to penetrate the cross-section until the whole cross-section becomes fully plastic. Beyond this point, at strains beyond this point, we experience no increase in stress. As a result of this, the stress-strain curve reaches the yield point and then becomes perfectly horizontal. To simplify things further, in plastic analysis, we ignore the curved nonlinear section between first yield of the outer fibers and full plasticity, and we assume the stress-strain curve becomes horizontal immediately at yield. This is sometimes simplified further, where we assume what we call rigid plastic behavior, where the cross-section is immediately fully yielded.